I went over a few things. So yeah, I'll take questions, but first let me quickly recall. We are working with graphs, and I said that undirected multiple edges, loops allowed, all that I said. But by and large, just think of simple graphs, meaning there are all the edges, there are either one edge, no loops. That's more or less any proof can be generalized to this level. There's not a big deal. But when writing, I will just do that, I think, henceforth. Associated matrix, we saw the adjacency matrix where you have a 1 if I and j form an edge and 0 otherwise. And so diagonals, if it's a simple graph, zeros on the diagonals and all edges will be 1. If it's a multiple graph, you have to put the multiplicity of the edges. So you take the degrees of the edges of the vertices, which is the number of edges connected to a vertex, and then form this matrix D minus A. That is, you take the diagonal di's and off diagonals are minus aij's. So then you see all the row sums and column sums are 0. Okay, you'll have d1 on the diagonal, and then you have minus 1 how many times, how many ever edges there are. So this will have row and column sums equal to 0. So, and this Laplacian therefore has the property that L applied to the constant vector is 0. It's a singular matrix. But it's
One
also
second. Can everyone see the screen, shared screen? I'm not able to see
No,
it.
I'm also not able to see it. So I was
okay.
wondering, I was
Okay.
just.
I've not even shared it. Sorry. I mean, now I realize. Sorry about that. Okay, sorry about that. So now I have shared. Can you see?
Yes.
Okay. Yeah. So I defined the graph, adjacency matrix, Laplacian matrix. Laplacian is a positive semi-definite matrix. As Kaushik pointed out, so there may be a factor of half here, but it's positive. So basically, LU inner product U is summation UI minus UJ square. If it's a simple graph, over all edges, it's the gradient square. I mean, the difference on the two endpoints squared. Okay, so that is what it is. So if you look at so the thing is, we will work henceforth with d-regular graphs. Okay, that's what we are going to do from now on. I'll just restrict myself to d-regular graphs, in which case these things can be related in a simple way. They actually have similar information, L and A, but they are not, if you want to look at, say, spectrum and so on, the relationship is not necessarily definite, because if DIs are different, then scalar matrix minus a matrix, we can't say much. But if we take a d-regular graph, then L is D times identity minus A. So eigenvalues of A, if it's lambda is an eigenvalue of A, if and only if D minus lambda is an eigenvalue of L. So that way we can transfer things easily. Actually, some things are better stated in terms of Laplacian, some things better in terms of adjacency matrix. But if you restrict to d-regular graphs, you can transfer both ways. In fact, there is one more thing that people often consider. Let me just mention it here. There's also this thing called the normalized Laplacian. Where is it? So there's also what is called, it's not, oh, okay, sorry, this is tablet is not connected. Right, okay, so there is also the notion of normalized Laplacian. Which is script L, which is, instead of this, you take d to the minus half L d to the minus half. What it is that it is basically, it has ones on the diagonal. And here you will have minus aij over square root di dj. That's what it will have. It's also a symmetric matrix. This is called a normalized Laplacian. As long as I restrict to d-regular graphs, this also becomes simple. This is just 1 over d times L. Script L is 1 over d times L. Okay, so that's where if we restrict to this, all some things are better stated in terms of normalized Laplacian, some in terms of Laplacian, some in terms of adjacency matrix. But for d-regular graphs, all these can be transferred to each other. So the key thing that I introduced last time was this expansion coefficients, which is the, for any set with size not more than half the graph, you look at the number of edges that go out and divide by the size of the set. Okay, so that is the expansion, and you take the minimum over all sets, that is, but only over subsets of size less than half of the full set, full graph, full vertex set. So that is what is called the expansion coefficient of the graph. And what we wanted was expander graphs. What we are looking for expander graphs, which is a sequence of graphs such that become larger and larger, and the expansion coefficient stays bounded below. It doesn't go to zero. So it's like the hyperbolic graph where the expansion coefficient is bounded below. But the maximum degree should also not go. If we don't drop this, then we have easy examples like the complete graph, which has expansion, which is in fact growing. The expansion is, EG is in this case something like n by 2 or something like that. It's in fact growing. But we cannot, we want the maximum degree to be D. So by the way, you can always notice that. So a point that I didn't make last time, observe that HG is less than equal to, see what is the max you can have. So the each of the air is less than equal to the max degree. Okay, it can never be more than that, because from each vertex in S, how many, at most this many edges can come out if max D, right? So this is at most max degree times the size of S. So if you divide, you get that it is at most this. So you cannot have, if I put the bound on the degrees, then you can't have something going, for example, not like n by 2. This only happens because the degrees are going like n. So that is the point here. So we want all this, and we saw that a few examples you might think of, they don't work. It is very tempting to put down an example, but it's not obvious. One can play a little bit, and it's not obvious that such things exist. A graph, sequence of graphs such that the size is going, maximum degree stays bounded, but the expansion coefficient is bounded below. That's the key point we were interested in. I'll not start on this one, but now I want to do a little bit on this expansion and so on. And one more point about the expansion I said last time was that, so one point to realize is that, so maybe just expanding on this, we saw this, that you can start with any x and the ball of radius x r plus 1 minus the ball of radius xr, the cardinality of that is h over d times this, at least that much. As long as this is not of size. So that's the expansion. So you see that the balls are going exponentially fast up to a certain point. Okay. So as a corollary of this, so let me leave it as exercise. So one is in general. So if max degree less than equal to D, then the diameter can be at most log of diameter cannot be is at least log of n in general over a constant which depends on D. And two, if and it's also right. So there is one constant and another constant CDH log n. So what we showed here is that the diameter will be at most log n, but the constant depends on the degree, max degree, and the expansion constant. But lower bound is without anything. So this is a small exercise. Just I leave it there. Any questions, comments so far? So I just quickly went over what I did last time. So now what I want to talk about first, before going into any of this, I want to talk about expansion and spectrum. So we are in this setting G equal to VE, and then HG is the min over all S less than equal to S by 2. S is a subset of the vertex set of the number of edges going to complement divided by the size of S. And then the eigenvalues, so AG LG has eigenvalues. So we saw that LG has eigenvalues 0, okay, and then less than equal to, let's call it lambda. This second one is the most important one. Let's call it lambda 2 less than equal to lambda 3 and so on. Lambda n, this is lambda 1. Okay. So this we will denote lambda sub g. Okay. So this is an important one. So when I say lambda sub g, this is what I mean. So correspondingly, we know, so we stick to D regular. Okay. So we'll assume D regular. So then these eigenvalues are D minus 0, D minus lambda 2, D minus lambda 3, and so on. Okay, those are the eigenvalues of the adjacency matrix. So there is a relationship between, there is strong relationship between the eigenvalues, so the spectral properties and the properties of the graph. This is something about the properties of the graph. So what we want to first say is that there is a relationship between graph properties and spectrum. This is one of the beautiful things in this this whole subject is called spectral graph theory. It's very nice. So we will see something. So first, a very simple one. Let me tell a very simple one. Simple observations. So one of them is that this lambda 2 is 0 if and only if G is disconnected. Okay, so lambda 2 is 0 if and only if G is disconnected. Okay, so that is one of the basic points. So you see that is there. Why is this? I mean, in fact, we will see more. Okay, what has this? So this connectedness disconnected of a graph is a graph property, and here we are saying something in terms of spectrum. Why is this true? Very simple, because remember LV inner product V for any vector is Vi minus Vj square I adjacent to J, probably with a half. Okay, so let's write half or no half, it doesn't matter. Therefore, LV inner product V equals 0 if and only if Vi equal to Vj for all edges I. Okay. So whenever there is an edge, there should be it should be so V is, that is, so this V is locally, so that is, this is same as saying V is constant on each connected component. Right? If Vi, any two adjacent vertices should have the same value, means on each connected component you have one value, right? Because so if graph is connected, there is only one connected component, so there is only one such V, namely the constant one. So,
Sir, question.
Yes, go ahead.
V was the vector that we multiplied, like we multiplied V with L, right? Like what was V again?
V is any vector for any V. Then if you want, you can think of it as R to the vertex set if you want. It's a function on the vertices. So vectors, we will think of either as functions on vertices or as vectors indexed by 1 to n. So either way. So LV inner product V is just that. So here I got LU inner product U is di ui square minus summation aij ui uj. So it was this, right? So I'm just, as I said, I will just think of simple graphs and write the thing. You can work it out for the general case. Is it clear or no?
Yeah, but I did not understand how you concluded that if Vi is Vj, then as in how that word, that some vector, right?
No, this is sum of squares, right? If this is non-negative, the only way it can be 0 is if each term is 0. These are non-negative terms. Each.
Yeah, I know the last implication. Why V is constant. So what is the connection
Okay.
between V and the connected components?
Right. So when anytime two adjacent things, so connected component means what? So if your graph consists of some pieces, so if this is a connected component, you can, it has to be constant there because these two values are same. V1 equal to V2, V2 equal to V3, V2 equal to V4, V4 equal to V5. It has to be constant on that, right? Each connected component. So if the graph is like this, here, anytime you have an edge, you cannot change the value of V, right? If I is here and J is here, Vi equal to Vj. So on this entire connected component, V has to take one value. The value of the V1, all the Vi's are the same. On this connected component, all Vi's are same, but there is no need that these two have to be same.
Okay, because the summation is over all the edges where I and J are
Yes.
connected.
Yeah, only when you have edges, so Vi equal to Vj when I is adjacent to J. So that means on each connected component, Vi has to take the same value. And for disconnected components, you may have different things. In fact, if this shows, in fact, what we have said shows that the multiplicity of zero eigenvalue is equal to number of connected components of G. Is equal to the number of, that's exactly follows from here. So if the multiplicity is 1, that means G has one connected component. Is that okay? So you get it from here. So once you have different connected components, you can take how many different bases I have. I can take one constant vector here, one constant here. For example, you can take all one vector here, 0 elsewhere. All one vector here, 0 elsewhere. So you get the basis is just how many ever connected components you have. So this is immediate from here actually. Any questions here?
Obvious question. In the sense, multiplicity of zero eigenvalue, is that the same as the null space dimension?
Yeah, exactly. Yeah, exactly. That's the kernel, the null space dimension of L. So connected graphs will have only one thing in the kernel, namely constant vectors. Okay, because constant is always in the null space of L, and so L of 1 is 0. For connected graphs, that is the only thing. Meaning that means only constant vectors are the ones that are null vectors. There's another one, not important for me, but it is sometimes comes. So a lambda n. Well, okay. So right. So here. Yeah, lambda n is equal to d, is equal to 2d. That is the minimum eigenvalue of A. See, if you look at A, this looks a bit unnatural. Here in terms of A, the largest one is d. If the smallest one is minus d. Lambda n is always less than or equal to 2d, by the way. So d minus lambda n is greater than or equal to. So all the eigenvalues are in minus d to d with equality if and only if the graph is bipartite. Okay, so the eigenvalues of A, because so the eigenvalues of A are in minus d to d. Okay, so these numbers are in, there is always one eigenvalue at d, and there are many other eigenvalues. The lowest one could go all the way to minus d, but that happens if and only if the graph is bipartite. That is, you can split it into two parts where the edges go from one to the other. I will leave that as exercise. I don't need it, but I mention this because this is the way you often see. So sometimes, so okay. So anyway, we'll come to that point in a moment. So sometimes in Markov chains, if you see Markov chain, if you have studied Markov chains, the largest eigenvalue is 1. And the smallest eigenvalue is below, could be -1 or above -1. It can't be below. And when it's -1, you usually have this periodicity question and so on. It's the same point really here. Okay. So because of this, sometimes so anyway, so this is there, but now I want to go for more quantitative points. Okay, so now more quantitative. This is one of the most fundamental theorems in the structure of graphs. Okay, so this is called Cheeger inequality. So we'll go more quantitative. See, this is only saying that lambda 2, for example, look at this. Lambda 2 is 0. This one is what I want to make quantitative. Lambda 2 is 0 or not 0. Even if there is very loose connection. So for example, if I have a graph like this, but there is a sort of a weak, weak connection. There are some bottlenecks, let us say. So there is some weak connection. It means it's kind of weakly connected in the sense that here you have a densely connected graph, but they are very weakly connected. In that case, lambda 2 will be non-zero. But what we want to say that lambda 2 will be small if the connection is weak. That's the quantitative statement. And this is the Cheeger-Boozer inequality. So trying to make that quantitative. Before that, are there any questions? Is it kind of clear? So I have left this as exercise. This I'll just leave as exercise. I mean, it is not going to be very important to me, though it will be important in spirit in a way you will see in a moment. So the Cheeger-Boozer inequality tells us that there is actually this lambda g, this lambda 2 is actually related to h in a very precise way. I mean, there is an inequality. So G is a deregular graph. Then, just give me a moment, 1 second. Sorry, yeah, so lambda g is related to h in this way. So on the one hand, it is at most 2 times the expansion constant. On the lower side, it is bounded by 2hg square over 2d. Okay, so this is the, yeah, so this is the one side. This is mainly Cheeger inequality. One side is in easy one. So this is the Cheeger inequality, this one. Okay, so it's a non-trivial inequality. So it tells you, for example, what it tells you is that so if Gn is so one of the points for us is that Gn is a sequence of expanders. Deregular expanders, if and only if lambda g. So it is, so by definition, this means hgn is bounded below. So I made the degree constant. So that is.
Sorry, what is lambda g? The lower,
second,
which one?
Yeah.
Second one, okay.
Second of the Laplacian. Okay, so that is going to remain for me lambda g. Okay. Yeah, so to say hg is bounded below is same as lambda g is bounded below.
Sir, in the statement, the theorem statement doesn't have expanders, right?
Theorem statement doesn't have
expanders. It is for any.
It has nothing. This is completely general. This is completely general. There is nothing about expanders here. It is a relationship between the expansion coefficient of a graph and the second eigenvalue. So what I'm saying is that from point of view of expanders, what we wanted was a sequence of graphs with expansion coefficient bounded below. But by these inequalities, you see it is same as saying that the second eigenvalue is bounded below, nothing else. It's the same. Because hgn goes to 0 means lambda gn goes to 0, vice versa. There is a bound in both directions. So one way to think of expanders is also to think of constructing a sequence of graphs such that the second eigenvalue doesn't go down to 0. Okay, so I removed all the degree condition by making it d regular. D is fixed. D is fixed. It's not changing. Okay, so is this okay? Is this clear? So this is very, I mean, this is one of the great inequalities. So it's a very beautiful one. So I want to prove it even, this has nothing to do with Fourier analysis, but this is great stuff. So this is actually, Cheeger is a very, very famous geometer. So the same thing is there in geometry. So you have what are called Riemannian manifolds. So say closed Riemannian manifolds. There is a notion of Laplacian on a closed Riemannian manifold. There is a notion of the second eigenvalue. So there will always be a 0 eigenvalue. Then there is a second eigenvalue of the Laplacian. And there is a notion of expansion in graphs, which is expansion in geometric situation, which is similar to what I showed you last time with hyperbolic space. In hyperbolic space, boundary to volume ratio is bounded below. So the minimum boundary to volume ratio is what is defined as the expansion coefficient of a manifold. And what Cheeger showed was that the second eigenvalue of Laplacian is controls the expansion coefficient. So the same proofs work for in the discrete setting of graphs. Much simpler, technically simpler. Any questions, comments so far? So let's see a proof of this. It's a very important one. So maybe I say a couple of other theorems and also then it will be more clear. So there is also, so the more it is bounded below, so better expansion is related to better bound on lower bound on lambda sub g. Okay, but there is a limit to how far you can go. That's another very important theorem in this subject. It is due to Alon and Boppana. That, so let's again take G to be D regular. Then it can't be too large. This second coefficient, it can't be too large. So it says that lambda G is less than equal to D minus 2 times square root of D minus 1 plus some, let me call it delta delta dn. So what is this delta dn? Delta dn is some quantity that goes to 0 as n goes to infinity for fixed d. Okay, so basically you cannot, so that is, in other words, the second eigenvalue of the adjacency matrix is greater than or equal to 2 square root d minus 1 minus delta dn. Okay, so the second eigenvalue of A is d minus that. So d minus lambda g is the second largest eigenvalue. I mean, here I mean the second largest. The largest is d. The second largest cannot be smaller than this 2 square root d minus 1 minus something that's essentially going to 0. So this is how this other definition comes. So this is where, so there is a definition which I will just mention. A sequence Gn of d-regular graphs is called Ramanujan So Ramanujan graphs. If this basically, if lambda, if basically this bound holds, if lambda gn is actually greater than equal to d minus 2 square root of d minus 1 for all n. So that means you cannot go much bigger than that, meaning the error you can't say d minus 2 d minus 1 plus epsilon. This thing will go to 0. But you want this. So these are the best possible expanders in that sense. Okay. So these are the best possible expanders in the sense of spectrum. That you can't do better than this in terms of spectrum. So these are the ones with the best lower bound on the second eigenvalue. So this so existence of Ramanujan graphs is another big problem. So this is even harder, much harder problem. Existence of Ramanujan graphs is even harder.
Sir, an side kind of question, like why Ramanujan, like did he work on this? Or?
No, I mean, okay, Ramanujan never, I think, used the word graph, but this was, it's a good question. So the reason is, it was first done by Lubotsky, Philip and Sarnak. So constructed for d equal to prime number or prime number plus 1 or minus 1 or something. Something like that. I forget now. So that they use the number theory heavily. Okay, they use number theory heavily, and it uses some conjectures of Ramanujan on what is called. There is a famous conjecture of Ramanujan on the divisor function. So it uses those type of things. So that's why they called it. They were the ones who called it Ramanujan graphs. So better now it was constructed by so recently. This was a big work of Spielman, Marcus. So Marcus, Spielman, and Srivastava. They constructed for all D. Okay, it's a somewhat randomized construction, but nevertheless, for any D, they could construct it. But Lubotsky, Phillips, Sarnak constructed it for prime P. So this is not a constructive one. It may be it's randomized, I believe. But this was a very big breakthrough in a quite recently. Like Nikhil Srivastava was here in Bangalore at Microsoft Research. Now he's at Berkeley. So this was a very famous piece of work. So this has no number theory or anything, but this has all these stable polynomials and all this type of stuff. Okay, so we'll not go there. We'll not go to Ramanujan graphs. We'll only stay with expanders. So, but you see that Ramanujan graphs are the best kind of expanders. You can't hope for more than this. Well, in the following sense, if I reformulate my, sorry, is there a noise? Do you hear? I mean, there is a, so there is some work going on here. That's why. So in terms of expansion, we are not saying this is best. We don't know. It's the relationship is not a linear one. It's somewhat indirect. But in terms of if you reformulate your definition of expander in terms of lambda gn being bounded below, then this is the best kind of expander you can hope for. And that is what is Ramanujan graph. Okay. Any questions, comments? Okay, so what I want to do today is maybe I will give a proof of this. Maybe I won't give a proof of this Alon-Bopanna. Okay, so this is maybe a bit complicated, but so let me do Cheeger inequality first, and then we will worry about the Alon-Bopanna here. Any questions, anything about this? So let's go for the proof. It's a very important theorem. Okay, so what we want to show is lambda g is bounded by 2 times the expansion coefficient and bounded below by hg square by 2d. Okay, so this is what for any d-regular graph G. So one way is actually easy. So let's do this lambda G less than equal to 2h G. This is actually easy. So what I need you to know is, I mean, I think everyone knows, but this is the point. So L is a symmetric matrix. Positive definite matrix. So 0 is the lowest eigenvalue. So L1 is 0, right? So then the thing is lambda 2, which is lambda g, this is lambda 2 equal to lambda g is, how do you get the second one? So this one, the first eigenvalue you get by minimizing the quadratic form. This you get by minimizing the quadratic form over all v not equal to 0, and v should be orthogonal to the first eigenvector, right? So this is something you may know. Relegates formulas for symmetric matrices. The smallest eigenvalue you get by minimizing the quadratic form. The next smallest eigenvalue you get by minimizing the quadratic form on the orthogonal subspace to the first eigenvector. Okay, and any v that achieves it is an eigenvector with eigenvalue lambda. Okay, so I hope this part is familiar to people. If not, I mean, this is more important than almost anything I ever say. So this is Relegate's formula. So what we do here is that, okay, so how do we get it? So easy. So take any S. Right, S contained in the vertex set. Okay, so I want to make a I want to make a vector. So I have the vertex set here, and let's say S is this. I want to define a vector. Basically, I want to make it 1 here and 0 there, but then it won't be orthogonal to the constant vector. So what I define is UI is 1 minus. So let's say the cardinality of S. Yeah, 1 minus the cardinality of S divided by N. And then here it is minus cardinality of S divided by N. If I is in S complement, if I is in S. So it is just the indicator S shifted by have 0 mean. So you take the indicator, you put the vector which is 1 on S and 0 outside. That's not orthogonal to the constant vector. So you just shift it so that it becomes 0 mean. That is orthogonal to constant vector. So then this is exactly because you will get 1 minus, let's say this is S, 1 minus S by N into S. And then minus S by N into N minus S, right? So U orthogonal U inner product with this is 1 minus mod S by N into plus minus, which is clearly that is what is 0. Okay, so it is orthogonal to the first vector, and you now calculate its coefficient. What is U inner product U? U inner product U. So let's call mod S as small s, just for simplicity of writing. Then it is 1 minus S by N squared. That comes S times summation UI square, right? And this S squared by N squared comes N minus S times. So if you just do this, so you'll get, what do you get? N minus S whole square. So you get 1 by S square, S into N minus S. And then yeah, you will just get this because you pull out s into n minus s, and then what is left is n minus. So it is exactly this actually. So it is s into n minus s divided by n. So which, by the way, is greater than equal to s by 2 if I take s less than equal to n by 2. As I want to take, you take any s with mod s less than equal to half of the size. So take any such s. So if s is less than equal to n by 2, then n minus s is at least n by 2. So this is at least s by 2. Whereas the quadratic form LU inner product U, what is it? It is summation ui minus uj square over I adjacent to j. Now you see that it only comes if, because it's constant on S. This is constant on S and constant on S complement. So only edges which are going across S will get any contribution. So you will get only over I in S, J in S complement and I adjacent to J. Only such edges will give you anything. And for such edges, you will get what? You will get the difference between these two, which is 1 minus 2s by n whole square. Right? Because any edge which is connecting two things in S, the difference is 0. Any edge connecting two things in S complement, the difference is 0. So there is nothing to, they don't contribute. So we get this. So what this is 1 minus.
No, is it 1?
Oh, sorry. The difference is 1. Sorry. Not 1 minus. Oh, yeah, plus this. So it is 1 actually. Sorry. The difference is 1.
And that makes sense. That will give you exactly that boundary of the thing, right?
Exactly. So this is the number of edges with connecting this. So from these two, what we see is that LU inner product U over U inner product U is actually, I have a lower bound for this. So this is upper bounded by, the top is equality, but the bottom is the UU is at least S by 2. So you'll get at least S by 2, which is, this is true. So this is true for all S. So, but this one, but this you know is greater than equal to lambda G. This is the relegates. What I mean is I have written here. So for any vector, LUU over UU is at least lambda G, right? So this is gives this, so which is 2 times. So for all S with size at most n by 2. So minimize over all S. So all of them are bounded below. So hence, that's all. So that's how the expansion, this inequality we have to. Any questions here? This is the easier part. We just plugged in for every S. We took the vector which kind of does this, and then which take the basically the indicator here and 0 here, and then shift it so that it's orthogonal to 1, and that's your vector. Plug that test vector into this relegates. You see that lambda j is bounded below by that. Is it okay?
Sir,
yeah.
Actually, this is all we need to construct a sequence of deregular expanders, right? Like, not the other bound is not needed.
True.
Because if we can lower bound lambda g, then that
no, that's true. That is right, but that's the other bound is very important. I mean, this is anyway. This is not. Don't even think of expanders here. This is a very fundamental theorem about structure of graphs, and so forget expanders. This is other side is also important. That lambda g is at least this much. So it tells you that these two are the same thing. Okay, so the expansion in terms of h or expansion in terms of lambda. I mean, in other words, constructing a sequence with lambda bounded below or constructing a sequence with h bounded below are the same thing. That's the same. Yeah.
Yeah, I mean, you might have mentioned this before. I can't remember, but if for a general graph, this hg is non-zero only if g is connected, right?
Right. Yeah, that is kind of true because, yeah, that's, I didn't say it, but it is also true. It follows from here if you want, because we showed that lambda g is 0 if and only if G is connected, but it is also obvious from the definition, because if you have a discussion,
because
then you can always pick the smaller of the two as S.
yeah, I think one of the components should have less than n by 2 vertices.
You can pick that as your S, and then you will see that the number of outgoing edges is 0. Right, that's true. So now we prove this. This is the other way. It's a non-trivial proof. I hope I will not botch it up entirely. So the idea is like this. So the point is, here you saw that the slack comes from the fact LUU is this is greater than equal to for every vector. So to go the other way, we take, so let V be an eigenvector with eigenvalue lambda g. So that is LV equal to lambda g V. Okay, so it's the second eigenvector. So we use that to construct the set S. We use V to construct the set S. So how? So we take, without loss of generality, label vertices. Sorry, I am using V for the, maybe I call this U. V is vertex set and also vector. So let's just call it U. Let U be the second eigenvector. So then LU is equal to lambda G times U. So just label vertices so that U1 less than, let's go the other way. It actually doesn't matter, but okay, let's U1. So order the vertices, so label the vertices so that U1 greater than equal to U2 greater than equal to up to UN. Okay. So by the way, U is going to be orthogonal to the first eigenvector. That is also clear. It's a second eigenvector. Eigenvectors are orthogonal. Yeah, remove the connected case. I mean, disconnected case. We only worry about a connected case. That's the only interesting part. So this is a distinct eigenvalue. So you will be orthogonal to 1, and you relabel the vertices so that this happens. So the claim is, and now take S to be the vertex set. You take, basically you take the first half of them. 1 second. 1 second. I'll just come. So take S to be the set 1 to K. Then, so the point is, this is basically, so this is a, if you want, a sub-level set of. Okay, just hold on 1 second. Hello. So basically, what I'm saying is I just label the vertices for ease of notation. But what we are doing is we take sub-level set of U. One of these will appear. In fact, S equal to K by 2 will do. I mean, K equal to N by 2. We divide it into about half. Okay, so you take that will do. So we will say that this will have a large this will have what we want to show is yeah, what do we want to show? Oh, sorry. Yeah, what is it? This will achieve yeah, so we'll get an upper bound for this. So we'll want to show that for this you get less than equal to whatever here square root 2 lambda g. So which of course implies this. because you have
bigger than equal.
no
Bigger or
Let's-
HG is the minimum of those, right?
right. So if you find one of them, then it follows that HG is smaller than.
Okay. Yeah.
So you just need to produce one set with small expansion. Small means relative to this. So we just show this, then it follows that HG is less than equal to this, which is less than equal to this. So this is the same as this. So that is the way to show. Now this proof is a bit tricky. It's not so obvious. So how do you do this? So first of all, you have this U. So let's write this vector U. We have U1, U2 up to UK minus 1, UK, UK plus 1, so on up to UN. Let's write the vector U like this. I define a couple of other vectors, X and Y. I define two vectors like this. X is going to be, so these are, these inequalities go this way, right? These are decreasing like this. So you take U1 minus UK, U2 minus UK up to UK minus 1 minus UK, then this is 0 and you put 0 elsewhere. So this is this part. Y will do the other way. It takes UK minus UK plus 1 dot 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 UK minus UN and you put zeros here. Okay. So if you look at, so this is what it is. So if you want X plus Y is just U minus UK. So X plus Y is U shifted by UK. So that is one point. So the U has been split into two parts. I mean, U minus the shifted. A shift of U has been split into two parts. Okay, so now what do you do? The point is we want to consider both. So what is norm U square? So norm X square plus norm Y square. If you look at norm X square plus norm Y square, it is sum of UI minus UK square. Right? UK minus UK is 0, that's not anywhere, but UI minus UK will occur here or here. So it is just this. But you know that this is less than equal to summation UI square.
That you need X and Y are orthogonal. That's why you have that, right?
X and Y are orthogonal. I don't know if that is exactly the way I will use it. Yeah, maybe.
No, but the norms inequality. Otherwise, you will have.
No, this is, well, I'm just directly writing norm X square is the sum of U1 minus UK square up to UK minus 1 plus UK square. Norm Y square is UK minus UK plus 1 square up to UK minus UN square. Here there is one extra term UK minus UK square, which is 0. I'm just writing the norm square directly.
Okay. Sir, isn't X minus Y equal to U minus UK? There is a minus because you wrote it as UK minus UK plus 1.
Right. Yeah, you are right. So X minus Y is this. Yes, that's correct. You are right. But X plus Y is the absolute value. Yeah, anyway, so this is not, forget this. So norm X square plus norm Y square, you write it directly, you see this, but here you are taking the differences of UI from one constant. You know that is always the best, this is greater than or equal to, not less than equal to. This is greater, when is it minimized? The difference squares. When you put UK equal to the mean of UIs, right? So you know that UI minus C squared is minimal C is the average of UIs, which in this case is 0 because U is orthogonal to the constant vector. It is 0. Therefore, this is actually, this goes the right way. Now, what I want is about L. So let's look at LXX and LYY. What is LXX? It will give me, so LXX will be sum over because these things are all in the S. S is 1 up to K. You remember S is 1 up to K. Okay. So when I do LXX, I get the difference xi minus xj over I adjacent to j, and then plus summation yi minus yj square over I adjacent to j, right? I mean, that's what these things are. But you see, this thing xi minus xj, so this means here both are inside S, otherwise you'd get 0. Oh, okay, sorry. No. What am I saying? Is I want a less than equal to, so yeah, when the so if I and j are in S, I get okay, so what happened when I and j are in S, this is same as ui minus uj square. Yeah, what do I get? Sorry, here I get these differences are ui minus uj, these are ui minus vj, but when I take in this and this, yeah, okay, so these are positive. Okay, so I want to say that this is over all I adjacent to j. See, xi minus xj, if both are here, then that is same as ui minus uj. But if I is here and j is here, the difference between xi and xj is smaller than the difference between ui and uj, right? Because these you have pulled up the u's. The difference between ui and uj is large between these two. So all the differences are larger here. So you get this. LU inner product U. So we got both way comparison. So what we get is that lambda G, which is in fact this ratio of the quadratic forms, LU inner product U over U inner product U, that is the, because this U is the second eigenvector. U is the second eigenvector, so this is equality. What we are saying is that this is greater than or equal to, the numerator is greater than or equal to Lxx plus Lyy, and the denominator is greater than or equal to xx plus yy. Is less than or equal to xx plus yy, so the inequality goes this. Okay, so this is what we get. So we get these two. Now the point is we'll use the bound. It is either bigger than Lxx over norm x square, minimum of the two things.
It's 1 o'clock.
Oh, it's already time. Okay, so yeah, so what should I do? It is this is true. A plus b over c plus d is greater than or equal to minimum of this. This is trivially true. So let's say without loss of generality, it is Lxx over norm x square. Okay, so you have to now relate this to the expansion of S. So far we have related lambda g to this. Lambda g is at least equal to this. So now we have to relate this to the expansion of S. So is it okay if I take a few minutes, or shall I just postpone it to next time? I mean, whatever. It's 1 o'clock. So
few minutes is fine with me. You can just ask.
Yeah, fine by me.
You can go ahead, Manju. I have some other meeting, so I have to go. But it's okay. I'll read it up.
Okay. Yeah, sorry. I mean, yeah, because next class also I want to just start on the proof of expanders. So I will just finish it up here and then, yeah. Okay. So, but anybody who wishes to leave, please feel free. I'll just finish the proof. You can always read it in books. So this is in many places. So lambda g. So we get this. So now we want to analyze Lxx over norm x square, which you remember is sum over I adjacent to j xi, right? Now what we do is we just multiply and divide by. This is the tricky part which I don't know how to motivate. I mean, somebody thought of this. You multiply and divide by this summation xi plus xj square. Now we can use, what we will use is, we want a lower bound for this. Okay, so lambda g is greater than or equal to this. We want further lower bound in terms of the expansion of S. So what we do here is that, so here we use Cauchy-Schwarz in the numerator. So this is sum of squares. This will be the product, the product and then square, right? So product is xi minus xj into xi plus xj. So this is xi square minus xj square. Sorry, there is no square inside. Xi square minus xj square. That is what you get, and then the whole square of that. And then below, what we can do is, so below xi plus xj square. So here this is Cauchy-Schwarz, and here we use that xi plus xj square is less than or equal to 2 times xi square plus xj square. So then if you sum over all I and j, xi plus xj square, you will get 2 comes out, and then you will sum over all I adjacent to j, or all edges xi square plus xj square. So how many? So that is 2 times just summation xi square, but each edge, each vertex comes d times because it is in d edges. So you get this. So you get 2d times summation xi square. Already I had one summation xi square. I have one more summation xi square, the whole square. So this is what you get. Okay. Yeah, so now what? Yeah, let me look up. So there is a small trick. Yeah, so what is it that you do now? Xi square minus xj square. Yeah, now we have to relate it to, yeah, quantity. So this is the square of something. So it is 1 over 2d. Okay, anyway, no point in writing that. So to understand this one, so look at the numerator there. The numerator is summation xi square minus xj square over all I adjacent to j. So what we will do is, we will write each of them as a telescoping sum. We have 1, 2, 3 up to n here, the vertices. So xi square minus xj square we will write as the successive differences of all these things. Okay. So now you look at, so each of them has only successive differences. So I get, let's call it xk square minus xk plus 1 square. How many times will it come? So you look at some k and some k plus 1. In what all I and j will that come? Any I, sorry, maybe I should call it L. Sorry, k was something fixed. So let's take some L and L plus 1. So when all will xl square minus xl plus 1 square come? If I is to the left of here and j is to the right of here. You agree? So if I is to the left of here and j is to the right of here. So how many edges are Si to Si plus Si complement? See how many edges are there between this part, between up to sorry, SL and SL complements. So any edge that has one vertex on below L and one vertex above L will contribute here. So that's what you get from L equals 1 up to N, like that, N minus 1. Okay. So now you can say that, okay, so this is greater than or equal to now we know that E of SL complement is greater than or equal to Hg times the size of SL, which is actually L, if you want, provided L is less than or equal to n by 2. Something like XL square minus XL plus 1 squared times L for L running up to n by 2. Okay. Yeah, what is this? So I want to just, yeah, what is the last part? Okay, sorry, I may have to look it up. Yeah, so what, yeah.
So SL is all the vertices up to index L because you ordered them, right? Is it correct?
Right. Yeah, SL is 1 up to L. SL is 1 up to L. So you get Hg times this sum, and now, yeah, so this one is what? It is L. This is more or less okay. This is actually okay. So should I take? Yeah, this is Hg times. This is more or less XL square because it comes once with a plus, once with a minus. Right, XL square minus XL plus 1 square times L. So XL square will come once with L, once with L minus 1 with a negative sign. So this is actually basically this. Okay, so maybe it was not that easy to follow, but the point is what we did was this numerator we have bounded below by Hg times this summation XL square. So what you get here, if I go back here, what I have shown is that this is greater than or equal to Hg square times XL square the whole square and divided by 2d times summation xi square the whole square. So this cancels, and that's what we wanted to show. So this last part is tricky. In fact, I had to read many times to do this, but this is so if you are interested in this, let me just tell, there's a nice, so there's a book by Fan Chung. Fan Chung is a very famous name in spectral graph theory. But there is a paper after her book. She has a book called Spectral Graph Theory, but there is a paper which says 4 proofs of Cheeger's inequality. Okay, so mainly the second part is the non-trivial part. So this one, proving this one. And all of them, I did not read it fully, but they are all of this kind. So you will take some particular vector. You have to choose a good vector. Like here, we chose it to be the second eigenvector. And you will take a sublevel set. So basically what we have got here is that from one of these sublevel sets is what is being for these sublevel sets. So one of them is, so all of the proofs are similar, that you will pick a particular vector and then choose the corresponding sublevel sets. But the choices of U are very interesting. They are different. This is the second eigenvector. In another proof, she chooses U as like this. You start a random walk at some point and run it up to some time and look at the probability and or take that vector and order that. So that is one. Another third proof is using this page rank algorithm. Page rank is a way to order the vertices according to some ranking that is used in all this Google search and all that. So she uses that page rank algorithm to find a particular vector and uses that page rank as the as the ordering to give an order, and again use the sublevel sets and so on. So there are multiple proofs. Okay, so maybe I will just end here. So next time I will just maybe start by saying a word about this Alon-Bopanna thing, and then go on to proof of existence of expanders. Okay. Okay, I'll stop here.